So how do I calculate the energy stored in a capacitor when it is charged? So if we close this capacitor here and we let it charge up, let's start off by looking at the energy supplied by the cell. So if we plot a graph of potential difference across the cell against charge, then what we get is a constant straight line for the cell because the cell provides a constant potential difference. And if I want to calculate how much energy is stored when I add a certain amount of charge, well, using the definition of potential difference is work done per unit charge. So if I do potential difference times charge, I get the work done. This is actually the area under the graph here. So if I want to figure out how much energy is supplied by the cell in order to charge the capacitor, I have to work out this total area up to the maximum charge Q. Okay, so this whole area, which is a rectangle. So it's just going to be V times Q. Okay, so that's going to be the total energy supplied by the cell. As an example, let's pretend we have a 6-volt cell and a 100 microfarad capacitor. So let me figure out how much charge I can store in this capacitor. So I will do 6 volts times the capacitance. So I'll get that using Q equals CV basically. So 6 volts times the capacitance, that gives me 6 times the minus 4 coulombs of charge I can store. Okay, then I'll just need to multiply that by the voltage, which is 6 volts, to get the total charge energy I can store, which is 3.6 millijoules. So 3.6 millijoules is actually the energy supplied by the cell. However, that's not the energy stored on the capacitor. To understand that, what the energy stored on the capacitor is, you look at the potential difference against charge graph for the capacitor. The capacitor initially started off with 0 volts and then it increased up to the maximum voltage, and it stops charging when the voltage across is the same as the potential difference of the cell. So it's the graph with the capacitor looks a bit like this, is a straight line, increase from 0 to the maximum V there. And the area under this graph is the actual energy supplied or stored, sorry, in the capacitor. So we need to calculate this area here. So let's start off by firstly figuring out, you have to figure out the charge that's stored, the maximum charge that's stored. And then, as you can see, it's a triangle. So it's actually going to be half Q times V. So only half of the energy that's supplied by the cell is actually stored in the capacitor. Let's take the example of our 6-volt cell and a 100 microfarad capacitor. So we calculate the maximum charge we can store in this scenario here, which is 6 times the minus 4 coulombs. So if we do half times the charge that we just calculated times the voltage, which is 6 volts, we get 1.8 millijoules. So we saw earlier on the battery supplies 3.6 millijoules, but the capacitor only stores half of it, which is 1.8 millijoules. Okay, so what happened to the other half? The other half of the energy, the other half, which is 1.8 millijoules, was actually dissipated in the resistor in the circuit, or any resistance in the circuit. So how do we explain this? Well, if you think about at the very start of the charging process, all of the voltage was actually across a resistor, and the voltage across the capacitor was 0 at the very start. And only when the voltage across the capacitor reached 0, then the resistor got 0 volts. So during that time, the resistor was dissipating half of the energy supplied by the cell. So this is a very useful equation to calculate the energy stored in the capacitor. But what about if you don't have charge and instead you have let's say capacitance and voltage? Well, you can eliminate charge from this equation by just substituting it in, and when you expand this, you get another very useful equation, which is energy stored in the capacitor equals half capacitance times potential difference squared. Okay, but what about if you don't have the voltage instead? So once again, just using Q equals CV, let's just eliminate that by rearranging it so we get V equals Q over C. And that comes from the definition of capacitance. And if we substitute that in and then expand this, we get half Q squared over C, which is, again, the energy stored in the capacitor. You can use any three of these equations based on which one is more useful. The capacitor is charged until it stores energy E. The capacitor is then discharged until the voltage across it is half its initial value. State the energy stored in the capacitor in terms of E. So first thing to acknowledge here is that as this change is taking place, we're not changing the capacitor itself. So that means the capacitance is a constant. So C here is a constant because we're using the same capacitor. Secondly, we've got the voltage, which is being decreased by half its initial value. So that means the voltage is being halved. And we're interested in the energy, E. So we're going to look for an equation for energy in terms of capacitance and voltage, because we know what's happening to those variables. So we're going to use E equals half CV squared. The half is a constant, the C is a constant, so I'm going to just rub those out because it's a proportionality question. And the voltage is being halved, so I'm going to times that by half, but that's being squared. So that whole thing is inside a square, which half squared is a quarter. So the energy is going to be a quarter of what it was before. Okay, so the E over 4. So this is important because this shows that as the voltage decreases, the energy actually decreases squared. So it decreases a bit more rapidly, if you can think of it that way.